Okay, what we're going to do now is we're going to just recap on the numbering system. So this one is just the basics of what you have studied before in digital logic. Nevertheless, this is actually very, very crucial foundation for the microprocessor subject. So have you all, that side, have you all seen the Mission Impossible box? Not yet. So pass to that side and the other side, have you all got it as well? Okay, for those who you can pass the other side. Is it recording?
Yep.
So we're going to see some of the main positional number system. If you see in this course, I'll be using a lot of abbreviations. So if you cannot understand what those abbreviations stands for, then please do stop me and ask what those abbreviation means. So basically, because we are dealing with the digital hardware, as I mentioned, for this course, we are dealing with microcontroller, which is manufactured by Microchip, and it's known as PIC 18 series. So we are actually learning PIC 18. That is the acronym that we actually use. So we are learning that particular model, and that is actually a digital hardware. So we're going to see what are those positional number system which is actually related to digital hardware. So here I've listed 4 numbering systems. The first one is, don't say December, decimal, binary, octal, and also hex. So what are the allowable digits for each numbering system? For decimal, what are the allowable digits? Actually from 0 until 9. It's actually decimal number. For binary,
0, 1.
easy, 0, 1. Octal, 0 to 6, 0 to 8, 0 to 7. Remember, because we are actually counting from 0. So it should be 0, 1, 7. Okay? And then we have hexadecimal number, right? So what's the range? It goes 0 until 9. After 9? You represent it with alphabet A until F. What is the value of F in decimal? 15.
15.
Always take note that because you are counting from 0, maximum should minus by 1. So decimal means 10. 10 minus 1 is 9 because you're starting from 0. So likewise with hex, it's actually 16 digital number. So minus 1 is 15. So because you're counting from 0. Is it okay? Now between this digital hardwares always work in this binary 0 or 1. Any digital hardware works on binary. We humans, we are decimal. What these two do? Now there is a relationship between this one and this one, and also this one and this one. Now they are known as natural correspondence or compact representation. What does NC stand for? Natural correspondence and also compact representation. We shall see what those means with respect to binary octal and so binary hexadecimal. Is it okay? Any question up to this point? Just recapping on. So throughout this course, there's one thing which I always tell repeatedly is that don't worry about writing down notes. So I immediately put on pen. I had to write. Right. So why I actually emphasize that don't worry about writing notes is that always worry about understanding first, then you can write. If you need time to write the notes, you can just let me know, sir, wait, I need time. Okay, I'll just give you time. So during the time when actually explaining some things, don't write. Listen, try to listen and try to understand. If you don't understand, immediately ask question. So after you've understood, if you write down, then the note has some value. If you write down something that you don't understand, then why are you writing down? No, it's a process, must write down notes. Then go back and study lah. You don't understand in class, what are you going to go back and study? Practically nothing lah. So always I tell students, you have to be smart in actually taking down notes. You should write down what you understand rather than writing down the notes and then later try to understand it. As I mentioned this class, I give importance for understanding. If you don't understand, ask question, and then if you need time to write, you can write. Is it okay? Yes. So whenever I am explaining certain things, put down your pen, hold on, don't worry about writing. Some students even better. Say, sir, can you move to the side? But don't do that. When you write something, then you actually learn more. So these are some of the numbering systems, and these are the allowable digits. So it's okay so far? So next thing is we're going to just see how do we actually convert from different base numbers. Now this is actually known as the base numbers, right? Different base numbers. So how do we actually identify these base numbers? We have the subscript right down there. This one it will be 10, this one will be 2, this will be 8, and this will be 16. So this is a subscript of the number. So when you have numbers like, for example, base 2, base 8 and base 16, we actually would like to actually also convert them to decimal. There's two numbering systems that we want to see how the conversion takes place. Other base numbers to base 10. So how actually we do this conversion? Now why we actually eager in converting other base numbers into base 10 is because we very easily understand base 10. We also have 10 fingers, so it makes it easier to understand base 10. Of course there are some other reasons as well why we actually want to convert them to base 10. So now the question is, how do we actually convert from other base to base 10? What do we do?
Use calculator.
With calculator. Okay, let's say for example, you have this binary digit, you know, from the base, and so if you want to convert this to decimal, how do you do that? Can you remember? Yes. What do you do? Yes, you multiply with the, multiply with what? 2. Multiply 2. In all numbering system, in all base numbers, every base number has a weightage. You all know that, right? Yes. In primary school, you have learned about Sa, Pulo, Ratus, things like that. I don't know how to convert that into English. I came from that education background, so internet students, kindly pardon me. That means every number has its own weightage. So in this case, because this is a binary number, every digit has a weightage of 2 by the power of the position, right? So this is 2 by the power of 0, 1, 2 and 3. So what you do is, you take this value, you multiply with the weightage of that particular digit. So in this case, what's the weightage? 2 by the power of 8 is? 2 by the power of 3, I just gave the answer. 2 by the power of 3 is? 8. So 8, and you know anything multiplied 0 is 0. This one? 2. Get back 2, and this one is 0. So you get a value of 10. And likewise, it also applies the same with base 8 or base 16. What you do? You multiply with the weights of that number. Now if this is binary, of course the weightage will be, the base number will be 2. If it's 8 means it will be 8 by the power of 0, 8 by the power of 1, 8 by the power of 2. And 16 means 16 by the power of 0, 16 by the power of 1, and so on and so forth. Is it okay? Yes. This is quite easy, so is it okay if I go to the next one? You all understand? what you have learned in secondary school and also logic, right? Quite simple, straightforward. Why is it straightforward? Because you are not never going to do this, you are going to use a calculator, right? During when I was taking this subject, calculator was not allowed. Someone in between made it allowable. Anyway, I never changed that. So likewise, we also would like to change this from base 10 to actually other base numbers. So how do we actually do that? How do we do that? If this is multiplied, the other one will be divide. You all still remember? No? Yes, Amir?
Yeah, no.
No, you. I thought you were asking question. No.
No.
So, you all know about the long division, right?
Yes.
So let's say, for example, here you have 8 by the power of, correct, 8 by the power of 10, base number decimal. You want to convert it to binary. So what do? You perform long division with the base number. So you take 8, you divide by the base number. So what do you write here? 4. Do you have any remainder? 2. What is this? 2. Of course, here is 0. I forgot. This one? Sorry. This will be
1.
the remainder?
1. 0.
0. And then? So how do you actually read this?
1. 0.
Which is the most significant bit? Most significant bit is always at the bottom, below. This is the most significant bit, this is the least significant bit. So what do you get? The resultant answer?
1. 0.
You get as 1, 0, 0, 0. You understand the principle, the concept? This is so likewise, if you have any decimal base number and you want to convert to octal, what do? You divide by the base number 8. Right? Same goes with the 16. You should divide by 16. Is it okay? Yes. Any question? Yes. 2. Here 1. Here 1. 2, 2, 2. Here 1. 2 times 2 is forward. Here remainder 1. Any other questions that you have? Is this okay? Long division? Okay, no, why not so blurry? Never did this before? Never did this before?
3 years.
3 years back. Oh, okay. Okay, so this is how you actually perform the conversions between any other base numbers to base 10 and from base 10 to any other numbers. Now remember that just now I mentioned about these two. Now this is how other base numbers are related to decimal. That means if you want to perform conversion, you must perform multiplication of the weightage. If you want to perform from decimal conversion to any other base number, you must perform the long division based on the base number. Now, just now I mentioned that there is a relationship between octal and hex with binary. So what is the relationship? So this now I mentioned something which is known as natural correspondence, right? So what is natural correspondence? So you'll see one example here. binary number, if you want to convert it to octal, how do we actually do the conversion? Now this is conversion, this is different. Just now from any other conversion to base 10 and base 10 to any other base number. Now we are doing from one base number to another base number. So how we actually do this? So what we do is, yes, you're telling something? Yes, you actually divide it into groups of 3. We divide into groups of 3, right? Correct?
Yep.
Why groups of 3? Come again? Come on, I can tell. Why groups of 3? Term. Yes. The maximum number of octal is 7. 7, if you represent it in binary, is 1, 1, 1. So that's very good. That's why we break into groups of 3. I remember doing this in secondary school. Correct, right? This is, we did this in Form 4. Modern maths, yes. So you break into groups of 3, and what you do? This is what is the equivalent? What is this value?
1 0 5 5 5
5. This one?
5
This one?
0.
Because you add up 0 in front, so you get a 0, so this is not really in the count. Zeros before a number has no value, but after number it has a value. So it will be equivalent to 55 octal. Is it okay? Now likewise we'll take another example. The same one. We want to convert into hex. So what we do now? Four bits. Why? Because hexadecimal is, what's the maximum number? 16. 15. So 15, you only require 4 bits, right?
1 1 1 1.
And this one you add the 0 in front. So this one, what's the equivalent value?
13.
So if you find it difficult to convert, always you can write down the weightage on top. 1, 2, 4, 8. So you can actually add up the weightage. So what are you getting? 13, right?
Yes.
13. No. Correct, 13. What is 13 in hex?
D.
Yes, it's D. Everyone got this? Anyone blur? You are following, you know. The side, this side. What is this?
2.
So 2. So now you're seeing things in
2D.
2D. Now, if you notice that this is what is meant by natural correspondence. That means from binary you can straight away convert it to octal, or straight away can convert it to hexadecimal number without performing the multiplication or performing the long division. It has a natural correspondence. That's what we mean by natural correspondence. It actually corresponds naturally. You just have to break them in the proper groups. That's what it means by natural correspondence. At the same time, I also use the word compact representation, right? What does it mean? Can you guess? Why is octal and hexadecimal is known as a compact representation of binary? Yes, simple answer. Be careful with this. See, the binary value is actually too long. When you represent it in hex or in octal, it becomes compact. So that's what it means by compact representation. Up to this point, is there any question or anything that you don't understand? These are basic things, right?
Yes.
What's happening?
Yes.
Can I move on? Can I erase the last one?
Yes.
Okay, so another thing that you must take into consideration is that for this subject, every single thing that you learn becomes accumulative. What do I mean by accumulative is that whatever we have studied now in numbering system, you need to apply in the next chapter. And the subsequent chapter requires the understanding of the previous chapters, and likewise. So it is an accumulative knowledge. So if you don't understand any portion of it, immediately you can ask a question. Is it okay? Now my advice is that if you don't understand any portion of the topic that we are going through, please make sure that you clear the doubt in the same week itself. So make sure you take a consistent effort to clear whatever doubts that you have in the same week itself. So do not prolong it. Because what happens is, in due course of time, you get accumulative doubt. Instead of accumulative knowledge, you have accumulative doubt. So when that time comes, it will be actually very, very difficult for you to catch up. Oh yeah, I forgot one very important thing to share with all of you. Upon telling this, all of you have the free will to actually drop the subject or change the section if you all wish to. So for this semester, unfortunately, I have a lot of outstation trips and a lot of overseas trips. So which means we will be losing a lot of classes. Nevertheless, we still need to make a lot of replacement classes. So, I'm telling all of you openly, I mean this semester I will be away a lot of times for overseas or outstation trips. So which means we need to have a lot of replacement classes. My question is, are you willing to take the replacement classes? Yes. So if you have problems, sir, you go overseas, I will go this other section. So no problem, I have no objection with that. You are a free country, free world, you are free to do anything. So I will inform you after checking all your timetables, I know when the free time. So rather than waiting until the end of semester, I prefer to have the replacement classes in the beginning itself. So last semester I told the students, I gave students option. Shall we do the replacement classes earlier? I said, no need, I don't need. End of semester, yeah, we'll see later. But then I gave them warning, okay, if you want end of semester, take note, at the end of semester you're going to have a lot of assessment and mini project, so don't regret. That one will worry, you continue. So at the end of semester, all of them are crying, so what you told is right. And I was laughing, So what we did is, now coming back to our topic of numbering system, we just recapped on what are the few numbering systems that we have which is used for digital hardware, and how to actually perform the conversion, because we are actually very much accustomed with decimal numbers, but at the same time the digital hardware works on binary. So most of the time we want to convert whatever values in decimal into binary. And sometimes the binary digit could be actually very long and difficult for us to interpret. And therefore we can use the octal and also hexadecimal numbers to represent them in such a way, in such a short format, and easy for us to actually interpret. So that two numbering system comes in handy when we want to actually represent binary, long binary number into a short compact representation form. Is it understood? Is it okay? So next we're going to see how to actually perform binary addition and subtraction. Now this is just a recap, so we're going to go very fast. So we have the binary addition here. So help me to perform this addition. 0 plus 1? 1 plus 1? What is 1 0 actually?
1 0.
2 is actually 2, right? How you get? This one? You get 3.
1
3 is actually 1 1. This one is 2. This one? You get 3. You get 2. You get 3. So this is carry. This is addition. Is it okay? So it's quite easy, right? It's just to go through only. Now how do you actually perform the subtraction? So help me. 1 minus 0? 0 minus 1? Now this guy want to borrow from here, this guy also doesn't have nothing, want to borrow from this guy. So when you borrow, this guy becomes, how much are you borrowing?
1.
Wait.
0.
10. Actually borrowing 2.
2.
Why 2? Yeah, because it's base 2 number. Same like if you notice that numbering system is actually a very interesting thing. In the primary or secondary you dealt with a decimal number system, right? Each time you borrow, how much you borrowing?
10.
10. Because the base number is 10. So this is base number 2. Each time you borrow, you can only borrow 2. Likewise, in also octal, you borrow means you borrow 8. In hexadecimal, you borrow means 16. Simple logic. Can you get it?
Yes.
So now you borrow 2. So this guy need to borrow from here. So you have 1. How much you borrowing? 2. So 2 minus 1? 1 minus 0? 7. 1 minus 1? So my brain works faster than my mouth, you know. Then this one? 0, this is 1. So this is the answer. Any questions so far? Is it okay if I use this combination of color? Can you all see those at the back and the side? Sometimes the different color is not easy for you to see. So based on your feedback, I know what color to use. If you don't tell anything, then I'll keep scribbling with whatever is there. Is it okay? What's this? Can I erase this one? So next topic that we are coming to is choose complement number system. First question, what is choose complement number system? Don't worry about writing, participate in the discussion first. What is choose complement number system? I've heard of it somewhere, but sorry, I'm telling you this as a lecturer. What is choose complement number system? Anyone? Any takers? Not even one. What happened? Say something, lah. Completely forgotten now. Very easy answer, right? I forgot it. It is like this. We pay you right? 50. So, choose complement number system is actually, you see, in digital hardware, for example, your PC is or your computer is how many bit architecture? 64. 64 is the new architecture, right? It's a 64-bit processor. Pentium 2. Then we have the slightly older one, it has a 32-bit architecture. And then the older, the compound one is 16, and then some more the older one is 8-bit. What does it mean? I don't know, sir. The bigger the number, the better. When you want to buy a computer, see, wow, 236,000 terabyte. So, see all this number, big number. This is a very good computer. How you know? All the numbers are big. The price is so big. Must be a good computer. How you know? Okay, what is 64-bit means? What means 32? What do it mean? Simply hantam by. So what it means that 64-bit and 32-bit means it can actually process 64-bit length of data at one time. So that means the architecture is actually done in such a way that it can process high data in a very fast speed. Now previously, that's why sometimes when you want to install certain softwares, there's actually, if you see program files, there are two, right? One is x86. x86 is actually the 32-bit architecture software. So the program that that program is actually designed for 32-bit architecture. Luckily 64 is supposed to, 64-bit processor can actually cater for 32-bit. But 32-bit cannot cater for 64-bit program. because the software is actually done to cater for 64 bits. When you install, you'll have the error. It's not compatible with this. Have you installed something like that? Which game? I mean, okay. So do you understand? When you want to, later when you become a developer, a program developer, you have a client, you will ask, you need to know the architecture. You want me to actually write the program for you for 32 bits or 64? So they'll tell you. So based on that, you need to design the architecture of the program. Is it okay? So lower than that is actually 16 and lower than that is 8. What it means, you can process 8 bits of data at one time. So the hardware architecture, the data bus, that means the pathway for the data is fixed. 32 bits means 32 bits. 64 means 64. 16 means 16, 8 means 8. Now for your information, the PIC-18 is an 8-bit microcontroller. 8-bit. For 8-bit also you start crying. So what it means that you can actually process the data length of 8 bits. So because the hardware is actually already, is already designed for 8. So now you cannot expand or reduce it. But at the same time, what we want to do is, we want to use these hardware architectures to compute certain arithmetic operations, right? Now you know in the real world there are positive numbers and there are also negative numbers. If we write simply just, if we write 10, we say it's a positive 10. When we put the sign negative here, we see now it is negative 10. Now, how do we actually represent, so in order for the hardware, digital hardware to actually able to perform real time, or I mean not real time, that's a different term, real computation, your digital hardware should be able to cater for both positive and also negative numbers, right? So how do we actually represent in a fixed data length? It's already 8-bit only. So that's where the 2's complement number system comes. Not sister, this is sister. 2's complement number system comes. So this 2's complement number system is actually used to express positive and negative numbers within a fixed number. You understand the statement? Right? That means now we are operating on 8-bit microprocessors, so that means we have only 8-bit fixed length. That's the 8 bits that we have. So within these 8 bits, we need to represent both positive number and also negative numbers. So how to do that is by using 2's complement number system. So let's say we have 8 bits. This is a fixed length, that means 8 bits. So how do we actually want to represent the positive and negative? Next question. So we use the convention of the most significant bit. What does it show us? If the most significant bit is 0, it is positive. If the most significant bit is 1, it is negative number. So these are known as sign numbers. So let's say if I write an 8-bit number like this, what is this value in decimal? It's actually 12, right? It's 12. So is this positive 12 or negative 12?
Positive.
That depends. Now there is two conventions used in numbering system. One is known as unsigned number. Another one is signed number. So this 2's complement number system is signed number. So what does it mean? Because normal binary looks like a normal binary. 2's complement number system is also operates on binary. If I give you this value like this, then I tell that this number is an unsigned number. So what do? You just convert this as a normal and you get 12. Right? You see. Now I am telling you that this number is a signed number. So what's the first thing that you should do? You should check for the sign. You should check for the most significant bit. Is it 0 or is it 1? So because the most significant bit here is 0, is this a positive number or negative number? It's a positive number. So when it's positive number, you can actually tell that it's positive 12. Now what happens if it's a negative number? If you have a digit like this, this one, if I told you if it's unsigned number, what do? You actually add up all the weightages on top, right? If I tell this is a signed number, you first have to check the most significant bit first, right? So this is 1, so this is negative. How do you find the value? Invert it. You perform 1's complement and then
Plus 1.
and plus 1. So you get the value. So we'll see that in a while also. Okay, we'll see that in a while how to actually convert negative number. So the thing that I want you to know now is there are two conventions of number. One is unsigned and one is signed. Now if it's unsigned, then you just, because both signed and unsigned and normal binary and also this 2's complement number system, they work on binary number. So the first thing is, if I say unsigned, what you do? You just take the weightage of the ones and you add them up, you get the value. But there's no sign to the value because it's unsigned. But the moment I mention signed, if it's mentioned, this question mentioned, this is a signed binary, means you should be alert to the most significant bit. Now if it's 0, you perform the same like normal binary. You just take the weightage and you add up, you get the equivalent. So you know that this one becomes positive 12. But then if you see that this is actually 1, you know that this is a negative number. For negative number, you cannot directly take the weightage. What do you have to do? You have to perform negation, right? This is a negative number. You have to perform negation to get the equivalent number. So you need to perform first complement. First complement means you toggle everything. So 0 becomes 1, 1 becomes 0. And then you plus 1. This is first complement. By adding 1, you mix it as second 2's complement. So this one will get 0. Now you see that it has become positive. So this process is actually known as negation. So whenever you perform 2's complement, is actually you are negating it. Negative number, when you multiply negative, what happens? It becomes positive. So once it's positive, what you can do now? You can take the weightage of the ones, right? So what is the weightage of the 1? This is actually 1, 2, 4, 8, 16, 32, 64, 1 to 8. 64 plus 16? Taking too long to think. Easy maths only, right? 4 plus 4?
84.
So long. 84, right?
84.
So you get
Next.
84. So you know that this number is actually negative. This is actually negative 84. Is it okay? So from here we know that if it's a sign number, immediately you need to check the most significant bit. If it's positive, you can just convert like you're converting normal binary. But if it's negative, you cannot directly convert, you need to perform negation. That means you're negatifying it. A negative number, when you negate, it becomes positive. So that you can know what is actual value of the negative number. So this is actually negative 84. Is that okay? Is everyone following?
Yes.
Okay, okay.
Okay.
Can I erase this one?
Yep.
I think my handwriting getting smaller and smaller. For the Muslims, what time we need to pray?
Right now.
Okay, we take a break. How long we need?
10 minutes.
10 minutes. Okay, we take a break. Even I think you want to. Yeah, the video is there.
Video, sir.
Sit. Pause.
Oh yeah, good.